Welcome to the Sleepy BrainDose. Here, you can let go of the day and drift into calm curiosity. Tonight, we'll journey together through the history of the universe, from its quiet beginnings to the stars, the galaxies, and the world we call home. You don't need to hold on to every detail. Just allow the gentle rhythm of science and story to guide you toward rest. You can let yourself settle gently now, as we drift toward the beginning of all beginnings. When we speak about the Big Bang, it is not a bang in the way of explosions we know, but rather a calm expansion, the unfolding of space and time itself. Imagine that everything you have ever seen, every star, every breath, every thought, all of it was once contained in a state so compact, so dense, that the very notion of size or distance had no meaning. There was no before, no place around, no outside. Time itself had not yet started its rhythm. And then, about 13.8 billion years ago, this stillness shifted into motion, and what we call the universe began. It is helpful to release the idea of fireworks or violent blasts. The word bang is a human attempt to capture something beyond our everyday images. In truth, the Big Bang was the expansion of space itself, a stretching of the fabric that would become the cosmos. It happened everywhere at once, because everywhere was just being created. In the first fraction of a second, the universe was smaller than an atom, and yet contained the seeds of everything that would ever exist. During those first instants, the conditions were extreme, far beyond anything we can recreate today. The temperature was trillions of degrees, so hot that matter as we know it could not exist. Instead, there was a sea of energy, a fluid of pure potential. Physicists describe this time in terms of quantum fields and symmetries, but for our gentle journey, it is enough to imagine a glowing haze, where distinctions had not yet settled. Time was only beginning to count its first moments, like the first slow beats of a drum that will continue forever. As the universe expanded, it cooled. This cooling is not like a breeze or shade, but the result of space itself stretching, allowing energy to thin out and settle into new forms. Within the first millionth of a second, the most fundamental particles, quarks, electrons, neutrinos emerged out of that primal energy. They are the building blocks from which atoms and eventually galaxies would form. Even then, the process was not chaotic in the sense of confusion, but rhythmic, guided by the consistent laws of physics that were themselves being established. One of the most remarkable features of this early expansion is its balance. If the universe had expanded only a little faster, matter would have thinned too quickly and no stars could ever condense. If it had expanded only a little slower, gravity would have pulled everything back into collapse almost immediately. But the rate was so precisely tuned that space could continue to grow while allowing matter to gather. It is as if the cosmos began with a delicate breath, steady enough to endure. In this early epoch, there was also a process known as inflation. It refers to a very short, almost instantaneous phase when the universe expanded faster than the speed of light. Not the objects within it, but space itself stretching at an incredible pace. In less than a trillionth of a second, the cosmos grew from subatomic size to something macroscopic, smoothing out irregularities and setting the stage for the patterns we see today. Imagine a balloon inflating almost instantly, yet imperfect. Quiet. That sudden expansion planted the seeds of galaxies, subtle fluctuations that gravity would later amplify. What is calming to notice is that the Big Bang was not an explosion into emptiness. There was no outside to expand into. Space itself was the thing unfolding. The distances between points grew, but there were no edges, no center. The universe did not expand from a single spot in the middle of darkness. It expanded everywhere, all at once. Even now, every point in space carries the memory of that first expansion, like a gentle echo. Scientists have confirmed this history through many kinds of evidence. One of the most persuasive is the cosmic microwave background, the faint glow that fills the entire sky. It is the cooled remnant of that early fireball, stretched into microwaves by billions of years of expansion. When you tune an old television to an empty channel, a small fraction of the static you see is literally this ancient light, still arriving after 13.8 billion years. In a very real sense, the night sky is bathed in the soft afterglow of the universe's own childhood. Reflecting on this, you may notice how the story is both immense and intimate. The iron in your blood, the calcium in your bones, the oxygen you breathe, all trace their origin back to those first instants. The Big Bang is not a remote event that happened far away. It is the opening chapter of the space and time that still surrounds you right now. In this quiet moment, and although the numbers are staggering fractions of a second, trillions of degrees, billions of years, the rhythm of the story is steady and gentle. The universe unfolded in a way that allows us to be here, resting, listening, breathing in calm awareness. The Big Bang reminds us that change can be profound without being harsh, that beginnings can be both powerful and soft. When cosmologists speak of the birth of time, they mean that before the Big Bang, before itself has no meaning. Asking what was there before is like asking what lies north of the North Pole. Time is not a container we move through, but a dimension that emerged with the universe. To rest in this thought is to realize that the cosmos is not inside something larger. It is the totality, the all-encompassing field of being dot in this vast picture. Our daily concerns, while important, find the context. The Big Bang offers perspective. From a state of unimaginable density and simplicity, all complexity has gently unfolded. From uniform haze, stars and planets emerged. From particles, people came to be. And tonight, you can rest within this lineage, knowing that the rhythm of your breath is part of the same unfolding as the rhythm of cosmic expansion. Let yourself imagine that expansion not as a violent surge, but as a soft ripple in the fabric of existence. Imagine it continuing even now, the galaxies drifting apart slowly, silently, like leaves on a calm pond. The same expansion that began with the Big Bang still carries on, and you are inside it, moving gently with it. The night sky is not just above you. It is a view into the ongoing act of creation. As we close this reflection on the Big Bang, notice the feeling of safety that can come from knowing that the laws of nature have held for billions of years, unbroken, guiding matter into stars and stars into elements, elements into life, and life into thought. The beginning was not fragile chaos, but a stable unfolding, one that still supports you now. In that recognition, there is space to soften, to release tension, and to allow yourself the calm that the cosmos has always carried forward. When the universe began its expansion, it was not yet a place filled with stars, galaxies, or even atoms. In those earliest seconds, everything existed in a state of pure energy and elementary particles, too hot and too dense to form the stable matter we know today. To explore these moments is to slow down time itself, to imagine the flow of events stretched so gently that we can follow each stage with calm attention. The very first fractions of a second after the Big Bang were dominated by unimaginable heat. The temperature was more than 1 trillion degrees, so intense that matter could not remain in solid, liquid, or even gaseous states. Instead, the universe was filled with a glowing plasma, a mixture where particles of light and matter moved freely, constantly colliding, dissolving, and reappearing. This was not chaos in the sense of disorder, but a fluid state of pure potential, waiting for the conditions to cool, just enough to allow structure. In this dense ocean of energy, the earliest particles began to emerge. Quarks, the tiny building blocks that would later form protons and neutrons, moved freely, unable yet to join together because the temperature was too high. Alongside them floated electrons and neutrinos, lightweight companions that would eventually play essential roles in atoms and reactions. These particles are so small that they cannot be seen directly, and yet they represent the foundation of all visible reality. As the universe continued to expand, it cooled. Cooling here does not mean air becoming chilly, but the thinning of energy as space itself stretched. Within the first millionth of a second, the quarks began to bond together, drawn by the strong nuclear force, one of the four fundamental interactions that guide the cosmos. This force is incredibly powerful at short distances, and it stitched quarks into pairs and triplets, forming protons and neutrons. These would later become the nuclei of atoms, the hearts of the matter we know. At the same time, particles of light photons moved rapidly, scattering off the newly formed matter. The universe was opaque, glowing with brightness, but without transparency, because light could not yet travel freely. Every photon encountered particles and was bounced in new directions. The entire cosmos was like a brilliant fog, dense with energy and movement, its rhythm more like vibration than open space. In these first seconds, another process was unfolding. Matter and antimatter were created together in nearly equal amounts. Antimatter is like a mirror twin of matter, with opposite electrical charges. When a particle meets its antimatter partner, they annihilate each other, releasing energy in the form of photons. For reasons still not fully understood, there was a slight imbalance in favor of matter, perhaps only one extra particle in every billion. That tiny excess was enough to ensure that after most of the pairs destroyed each other, a small remainder of matter survived. And it is from that small remainder that everything we see today exists. The galaxies, the Earth, and even you. This asymmetry, delicate and subtle, can be felt as a reminder of how finely tuned the story of the universe is. If the balance had been perfect, matter and antimatter would have canceled each other completely, leaving only radiation. No stars, no planets, no life. But because of the small tilt, an almost imperceptible bias, there was enough matter left to seed the cosmos with substance. By the first second of cosmic time, the universe had cooled enough for protons and neutrons to become stable. Within the next few minutes, these particles began to fuse together through a process called nucleosynthesis. The result was the formation of the first atomic nuclei, mostly hydrogen with some helium and traces of lithium. These simple elements would become the raw material of all future chemistry. Even now, the stars in the night sky shine primarily by burning hydrogen into helium, continuing the cycle that began in those first few minutes. Neutrinos, those elusive, nearly massless particles, also played their part. They interacted so weakly with matter that after the first seconds, they slipped away, streaming through space almost unhindered. Even today, trillions of neutrinos pass through your body each second, silent messengers from the earliest times. They carry with them information about those first moments, though they are difficult to detect. Their presence is a quiet reminder of the deep connection between your existence and the origin of the cosmos. The first seconds also established a fundamental balance between the forces of nature. Gravity, the weak nuclear force, the strong nuclear force, and electromagnetism all shaped the way particles behaved. Their strengths and properties have not changed since then. In a sense, the universe set its rules at the very beginning, and everything since has been the unfolding of those rules over vast scales of time and space. From a human perspective, the speed of these transformations is almost beyond comprehension. But if you slow the rhythm in your mind, you can imagine each stage as a gradual softening. Energy condenses into particles, particles bond into nuclei, and light begins its long journey toward transparency. Each phase is like a new breath in the life of the cosmos, gentle but unstoppable. Scientists have pieced together this history through experiments and observations. By recreating high-energy collisions in particle accelerators, they can glimpse conditions similar to those of the early universe. By studying the cosmic microwave background, they see the fingerprints of those first seconds imprinted on the sky. The story is not a guess, but a carefully measured harmony, confirmed through many lines of evidence. What is soothing to realize is that we are not separate from this process. The atoms in your body, the energy that allows your thoughts, all descend from those first seconds of creation. The protons in the water you drink, the neutrons in the calcium of your bones, have existed since those early times, unchanged. You are, in a very literal sense, carrying the memory of the first seconds within your own being. And although the events were immense and fast, the lesson they carry is one of stability and endurance. The universe emerged not as chaos, but as rhythm, guided by laws that continue without break. From that glowing fog, structure arose naturally, patiently, as if the cosmos itself was taking a deep, measured breath. As you reflect on this, you may sense a calm continuity. The first seconds of the universe were not just a remote past. They are still present in the matter around you. Every atom of hydrogen that fills the oceans or lights the stars has been here since then, unchanged, quietly enduring for billions of years. To notice this is to feel the security of belonging to something ancient and steady. The first seconds tell us that even in the most extreme beginnings, patterns emerge, order arises, and balance is preserved. They remind us that simplicity can lead to complexity, and that from the smallest fluctuations, entire galaxies will one day appear. And tonight, as you breathe slowly and allow your mind to rest, you are sharing in the same unfolding rhythm that began at the dawn of time. After the first seconds, the universe continued its steady expansion. It was still unimaginably hot and dense, but cooling with each passing moment. In this early era, energy was the dominant presence, filling every corner of space with radiation. Matter had begun to exist in the form of protons, neutrons, and electrons, but it was light that truly defined this age. For hundreds of thousands of years, the cosmos was a sea of brightness, not the starlight we see today, but a more uniform, ever-present glow. The universe was filled with photons, particles of light. Yet these photons could not travel far without meeting other particles. Every time a photon tried to move, it collided with electrons or protons, scattering in a new direction. Imagine being surrounded by fog so dense that light cannot pass through it. You would be immersed in brightness, but unable to see clearly. That was the character of the young universe, radiant, opaque, glowing from within, but not yet transparent. This state is often described as a plasma, a mixture of matter and radiation so tightly coupled that they behaved almost as a single fluid. The photons constantly exchanged energy with the particles of matter, keeping everything in equilibrium. For hundreds of thousands of years, the energy of light and the substance of matter were inseparable. The cosmos was not a dark place. It was saturated with luminous energy, a soft radiance filling all of space. During this time, matter existed mostly as free protons and electrons, not yet combined into atoms. The heat of the universe was so intense that any attempt of an electron to settle into orbit around a proton was immediately broken by the impact of a photon. It is as if the cosmos was too warm and restless to allow stable structures to form. The dance between matter and light was constant, restless but rhythmic, preventing the birth of atoms until the temperature dropped further. The dominance of radiation shaped the behavior of the universe. Gravity tried to pull matter together, but the pressure of light resisted. Photons, though massless, carried momentum, and their constant scattering exerted a pressure strong enough to counteract gravitational collapse on small scales. This radiation pressure kept the early cosmos smooth and uniform, preventing matter from clumping too quickly. It was as if light itself was gently ironing out the wrinkles of the young universe, keeping it even and balanced, yet within that uniformity, tiny irregularities existed. Slight differences in density, perhaps as small as 1 part in 100,000, were left behind by the quantum fluctuations during the phase of inflation. These minute ripples in the density of matter and radiation would later grow under the influence of gravity, becoming the seeds of galaxies and clusters. But during the era of radiation, these ripples were subtle, carried within the glowing fluid like gentle waves. As the universe expanded, the temperature continued to fall. From trillions of degrees in the first seconds, it cooled to millions, then to thousands. Around 380,000 years after the Big Bang, the temperature dropped to about 3,000 degrees Kelvin, similar to the surface of a cool star. At that point, the conditions finally allowed protons and electrons to combine into neutral atoms. This process is known as recombination. It marked a turning point because once atoms formed, photons were no longer scattered constantly. Light could travel freely for the first time. The moment of recombination was also the moment of decoupling between matter and radiation. Before this, the two were locked together, inseparable. Afterward, matter could move on its own, and light could stream across the cosmos without obstruction. The universe, for the first time, became transparent. The fog lifted, and the glow of radiation was released to travel through space forever. This ancient light is what we now observe as the cosmic microwave background. Today, after more than 13 billion years of expansion, that radiation has cooled to just 2.7 degrees above absolute zero. It is invisible to our eyes, but detectable with radio instruments as a faint microwave signal. It fills the entire sky equally in every direction, a reminder that the universe was once a uniform sea of light. When scientists map this radiation, they see not only smoothness, but also the faint imprint of those original ripples in density. Those tiny variations are the fingerprints of the first structures, the beginning of the cosmic web. Reflecting on this, you may notice how the story of radiation is one of transformation. At first, light was trapped, unable to escape. Then, with cooling and expansion, freedom arrived. Light was set loose, and the universe became open and transparent. In a way, this transition resembles the rhythm of breath, an inward holding, dense and contained, followed by an outward release, open and spacious. The cosmos itself moved through a similar cycle, holding its brightness until the moment came to let go. What is calming to realize is that the photons released at recombination are still traveling. They have been moving across space for nearly 14 billion years without interruption. Some of them are reaching Earth right now, entering detectors, or even passing through your body. Every moment, you are bathed in the gentle afterglow of the universe's own childhood. That light has never stopped, never faltered. It is the most ancient messenger we can receive, carrying with it the memory of the era of radiation, during those hundreds of thousands of years before atoms existed. The cosmos was not dark, but softly luminous. It was a brightness without edges, spread everywhere evenly. To imagine it is not to see a scene, but to sense a condition, a boundless radiance, neither blinding nor dim, simply present. It was the background against which all future complexity would unfold. Scientists sometimes call this phase the photon-dominated era. It reminds us that energy itself once held sway over matter. Only later did matter gather into stars and galaxies. In those early times, it was light that carried the rhythm, setting the tone for the expansion. To reflect on this is to realize that the universe began with radiance, and that radiance is still here, only cooled, stretched into microwaves. The era of radiation also teaches us about patience. Hundreds of thousands of years passed before atoms could form, before transparency arrived. From our human perspective, this may feel like a long wait, but in cosmic terms, it was only the beginning of a vast story. That patience laid the foundation for everything that followed, the formation of stars, planets, and life. Without the long glow of radiation, the cosmos would not have had time to smooth itself into balance. As you let these thoughts settle, you may notice the sense of continuity. The same photons that once filled all of space are still moving, unchanged, carrying the same energy, though stretched and cooled. They remind us that nothing is truly lost, only transformed. The light of the early universe did not vanish. It simply shifted into new wavelengths, becoming the quiet background of the night sky. To rest with this knowledge is to feel the safety of endurance. The glow of the cosmos has lasted billions of years, and it will continue far into the future. It is a constant presence, subtle but unbroken. In that recognition, you can allow yourself to soften, to imagine being held within that ancient light, just as the matter of the early universe was once held. After the long age of radiation, the universe entered a quieter phase. The temperature, once blistering, had now cooled enough to allow new structures to emerge. Protons and neutrons, already present since the first seconds, began to combine, with electrons creating the first neutral atoms. This was a turning point in cosmic history. It was the moment when matter took on a stable, enduring form, and when the elements hydrogen and helium were born. Hydrogen, the lightest and simplest element, is made of just one proton and one electron. Helium, only slightly more complex, consists of 2 protons, 2 neutrons, and 2 electrons. Together, these 2 elements would account for nearly all the ordinary matter in the universe. Even today, after billions of years of cosmic evolution, hydrogen makes up about 3/4 of all matter, with helium contributing most of the rest. Everything else, carbon, oxygen, nitrogen, iron, would come later, forged in the hearts of stars. But it was hydrogen and helium that provided the first building blocks. The process that led to their creation is called primordial nucleosynthesis, and it unfolded within the first few minutes after the Big Bang. As the universe cooled to a few billion degrees, protons and neutrons began to fuse. Because conditions were still hot and dense, these reactions happened quickly. The result was the formation of helium nuclei, along with tiny amounts of deuterium, tritium, and lithium. Yet hydrogen remained dominant, because not all protons found partners. Many stayed single, paired only later with electrons to form neutral hydrogen atoms. For hundreds of thousands of years, however, these nuclei floated freely, unable to capture electrons. The reason was simple. The universe was still filled with intense radiation, and photons had enough energy to knock electrons away from protons as soon as they tried to bind. Only after the temperature fell to about 3,000 degrees Kelvin, some 380,000 years after the Big Bang, could electrons finally settle into orbits around nuclei. This was the moment of recombination, when the first true atoms appeared. The emergence of atoms transformed the character of the cosmos. Before this, the universe was opaque, like a fog of charged particles and radiation. Afterward, it became transparent, allowing light to travel freely. This is why the cosmic microwave background exists. It is the very light released when the first atoms formed, stretched across billions of years into the faint radiation we detect today. In that light, we see the direct evidence of hydrogen. And helium taking shape. Hydrogen, though simple, holds profound importance. It is the fuel of stars, the source of the energy that makes them shine. Without hydrogen, there could be no fusion, no starlight, no warmth. Helium, in turn, is the first product of that fusion, the ash left behind when stars burn hydrogen in their cores. The balance of hydrogen and helium set by the early universe determined the destiny of galaxies and of life itself. What is soothing to realize is that the atoms in your body are directly connected to this ancient process. Every drop of water contains hydrogen atoms that have existed unchanged since the dawn of time. When you drink, you are consuming pieces of the universe's earliest matter. These atoms are not recycled or replaced. They are continuous, enduring for billions of years, participating in countless cycles, yet remaining the same. You carry within you the firstborn children of the cosmos. Helium, though less common, is equally remarkable. It is inert, stable, unwilling to form many chemical bonds. In this way, it represents peace and calm in the chemistry of the universe. Stars produce it in abundance, but the primordial helium, created in the first minutes of existence, is still with us. Every breath you take contains traces of that helium, drifting through the atmosphere since Earth's formation, unchanging and serene. During the age of the first atoms, the universe was simple. No stars had yet ignited, no galaxies had yet coalesced. The cosmos was filled with vast clouds of hydrogen and helium, spread almost evenly throughout space. These clouds were cool, dark, and quiet. Yet within them lay the potential for all. Future structure. Gravity would slowly draw them together, forming the first stars. Those stars would, in turn, forge the heavier elements, giving rise to planets and to life. But all of that depended on the first atoms, on the calm presence of hydrogen and helium drifting in the newborn universe. Scientists have confirmed this story through precise measurements. By observing the cosmic microwave background, they can see the ratio of hydrogen to helium imprinted in the early light. By studying distant, ancient gas clouds, they find the same pattern, about 75% hydrogen, 25% helium, with only traces of anything else. The consistency of these observations is striking. It shows that the universe began with simplicity, and that this simplicity has echoed across billions of years. To rest with this knowledge is to feel the continuity of existence. The atoms in the air, in your body, in the oceans and mountains, are not new creations, but ancient travelers. They have been here since the first atoms formed, moving through stars, planets, and life forms, but never destroyed. You are part of the same matter that filled the early cosmos, part of the same hydrogen and helium that lit the first stars. The story of the first atoms also reminds us that stability emerges from change. At first, the heat was too intense for atoms to exist. Then, as the universe expanded and cooled, the conditions softened and atoms appeared. It was not sudden but gradual, a natural outcome of the rhythm of cooling. In this way, the cosmos demonstrates patience. It waits until the time is right, and then new forms arise. As you imagine those early atoms, you may sense their quiet presence. Hydrogen and helium, simple and light, drifting through the vastness, unhurried. They were not yet part of stars or galaxies. They were simply there, filling space with potential. To rest in this thought is to notice the calm foundation beneath. All later complexity. Before life, before planets, before even the first star, there was simplicity, and that simplicity endures in every corner of the universe. After the first atoms formed, the universe entered a long and gentle age of darkness. There were no stars yet, no galaxies, only vast clouds of hydrogen and helium drifting through space. The cosmos was transparent for the first time, but without light sources, it was dark to the eye. This quiet interval lasted for hundreds of millions of years. It was not emptiness, but a waiting, a gathering, a slow preparation for the next stage of creation. In these enormous clouds, tiny irregularities in density, left over from the era of radiation, became important. Some regions were just slightly denser than others, so slight that the difference was 1 part in 100,000. Yet gravity, subtle but persistent, began to pull matter more strongly in those denser areas. Over time, atoms drifted closer together, forming clumps. Those clumps grew, attracting more matter, until they became massive clouds, the cradles of the first stars. The process was slow and patient. Gravity pulled inward, but radiation and heat resisted, pressing outward. For millions of years these forces balanced until enough matter gathered for gravity to win. As the clouds collapsed, the gas inside them heated up. The temperature rose to millions of degrees, and deep in the cores, conditions became extreme enough for nuclear fusion. To begin, fusion is the process where hydrogen atoms merge to form helium, releasing energy in the form of light and heat. It is the engine of stars, the reason they shine. When the first fusion reactions ignited, the universe changed forever. Darkness was broken by points of light, the first stars flickering into being. For the first time since the Big Bang, the cosmos was illuminated from within. These early stars, called population 3 stars, were unlike the stars we see today. They contained only hydrogen and helium, with almost no heavier elements. As a result, they were often enormous, many times more massive than the Sun. Some may have lived only a few million years before exhausting their fuel and collapsing. But during their brief lives, they shone intensely, flooding the surrounding space with radiation. The birth of these stars marked the end of the cosmic dark ages. Their light rayonized the hydrogen gas around them, breaking apart the neutral atoms and making the universe more transparent once again. Their ultraviolet radiation spread outward, clearing away the fog and allowing space to become bright and open. In this way, the first stars transformed their environment, shaping the conditions for galaxies to form. It is soothing to imagine this transformation not as sudden or violent, but as gradual. For hundreds of millions of years, the cosmos had been quiet, filled with drifting clouds. Then, one by one, stars began to appear. Each new star was like a small flame in an immense night, adding to the gentle glow. Over time, the number of stars grew, and galaxies began to take shape. The darkness became sprinkled with light, as if the universe had opened its eyes. The energy from these first stars also carried seeds for the future. In their cores, hydrogen fused into helium, and helium fused into heavier elements. When the most massive stars ended their lives, they spread those elements outward, enriching the surrounding gas. Carbon, oxygen, nitrogen, and iron all of. These came later from the hearts of stars. But the first step was simply the creation of starlight, the ignition of hydrogen and helium into shining suns. From a human perspective, starlight is one of the most familiar features of the night sky. Yet when you look up, you are seeing a legacy of this ancient transformation. Every star you see is part of a lineage that began with those first stars more than 13 billion years ago. The sky we find comforting and beautiful is the direct descendant of that moment when darkness gave way to light. The first stars also remind us of scale. They were vast, short-lived, and powerful. Yet they were also fragile in their own way, exhausting themselves quickly. Their deaths scattered the first heavy elements, allowing later generations of stars to form with more complexity. In this cycle of birth and death, the cosmos began its long rhythm of renewal. Each generation of stars built upon the last, enriching the universe with new possibilities. Scientists study the birth of stars through both observation and theory. By looking at distant galaxies, they can see light that has traveled for billions of years, capturing the glow of stars forming in the early cosmos. By using computer simulations, they can model how gas clouds collapse under gravity, showing the slow, patient process that leads to ignition. The evidence aligns with the story. The first stars arose a few 100 million years after the Big Bang, lighting the universe and shaping all that would follow. What is calming to realize is that the atoms in your body carry the imprint of this process. The oxygen you breathe was made in stars. The calcium in your bones, the iron in your blood, the carbon in your cells, all of it was created by fusion in stars and released into space when those stars ended their lives. You are, quite literally, made of stardust. The birth of stars was also the beginning of the possibility of life. To rest with this thought is to feel continuity. The same processes that lit the first stars are still at work today. In star-forming regions of our galaxy, new suns are being born from clouds of gas, just as they were in the beginning. The cycle has never stopped. You live in a universe that is alive with ongoing creation, where the rhythm of gravity and fusion continues endlessly. The birth of stars shows us that light emerges naturally from darkness. It is not forced or sudden, but the result of slow gathering, patient accumulation, and steady transformation. In the same way, your own life carries rhythms of waiting and emergence, of preparation and illumination. The stars remind us that even in long stretches of quiet, change is happening, and light will eventually appear. As you imagine those first stars, allow yourself to see them not as distant or abstract, but as part of your own story. Every breath you take depends on elements forged in stars. Every thought you have relies on energy released by the sun, itself a descendant of earlier stars. You are connected to that first ignition, to that moment when hydrogen and helium became light. The universe began with darkness, and then it made stars. You are part of that unfolding, part of that same rhythm of emergence. To notice this is to feel both small and vast at once, grounded in the immensity of time, and comforted by the steady glow of starlight. When the first stars were born, they did not remain alone for long. Gravity, the quiet and patient force, continued to pull matter together, gathering stars into larger structures. These structures are what we call galaxies, immense communities of stars, gas, dust, and dark matter, bound together by gravity's embrace. The formation of galaxies was the next great step in the unfolding story of the universe, turning scattered points of light into grand patterns that stretch across the cosmos. In the beginning, the universe was filled with hydrogen and helium. with small ripples in density. As stars began to ignite, those ripples deepened. Gravity amplified them, drawing more matter toward the denser regions. Over millions of years, these regions grew into the first galactic clouds. Within them, stars, formed in clusters, not in isolation. They gathered like families, held by the collective pull of their shared mass. These first galaxies were smaller than the great spirals and ellipticals we see today. They were irregular, clumpy, and dynamic, constantly colliding and merging with one another. But over time, through countless interactions, they grew larger and more structured. This is the way of galaxies. They are not static islands, but evolving communities, shaped by the steady rhythm of mergers and flows of gas. A galaxy is vast beyond ordinary imagination. Our own Milky Way, for example, contains hundreds of billions of stars and spans about 100,000 light-years across. That means light, moving at its constant speed, takes 100,000 years to cross from one side to the other. And yet the Milky Way is only one among trillions of galaxies. In the observable universe, each one is a vast community with its own history, its own shape, and its own rhythm. The shapes of galaxies tell their stories. Some are spirals, like great pinwheels, with arms curving outward from a central bulge. These arms are sites of ongoing star formation, glowing with the blue light of young, massive stars. Others are ellipticals, smoother and more rounded, filled with older stars and little gas. Still others are irregular, shaped by collisions or incomplete growth. The diversity of galaxies reflects the diversity of their paths. No two are exactly alike, just as no two human communities are the same. What is soothing to realize is that galaxies are not isolated. They, too, live in groups and clusters, bound together on even larger scales. The Milky Way is part of the local group, a small cluster of about 50 galaxies, including the Andromeda Galaxy and the Magellanic Clouds. These groups form part of larger structures called superclusters, and even those connect into filaments, weaving the cosmic web that spans the universe. Galaxies are communities within communities, layers of structure unfolding outward. Within galaxies, new stars are constantly being born from clouds of gas. Old stars die, returning their material to the interstellar medium. This cycle of birth and renewal is the heartbeat of a galaxy. Over billions of years, the gas becomes enriched with heavier elements, creating more complex chemistry. Planets, and eventually life, arise as part of this galactic evolution. The galaxy is not just a collection of stars, but a living system. Evolving with time. At the center of nearly every galaxy lies something even more mysterious: a supermassive black hole. These black holes can have masses millions or even billions of times greater than the Sun. Though invisible, they influence the behavior of their galaxies, shaping the movement of stars and the flow of gas. Sometimes they flare with energy as matter falls into them, outshining the entire galaxy for brief periods. Other times they rest quietly, as in the case of the black hole at the heart of the Milky Way, called Sagittarius A*. These central black holes remind us that galaxies, like stars, have inner depths still waiting to be understood. Dark matter also plays a crucial role. Though invisible and undetectable directly, its gravitational pull is necessary to explain the way galaxies move and hold together. Without dark matter, the outer stars of galaxies would drift away. Instead, they remain bound, evidence of a hidden mass surrounding each galaxy like an invisible halo. In this way, dark matter provides the unseen framework upon which galaxies form and evolve. It is the silent scaffolding of the cosmos. To reflect on galaxies is to feel both awe and comfort. Their scales are immense, but their story is steady and comprehensible. They form from gravity's patient gathering. They grow through collisions and mergers. They shine with the light of countless stars, and they endure for billions of years, continuing their cycles long after individual stars have lived and died. When you look up at the night sky and see the Milky Way stretching across the darkness, you are seeing only a glimpse of this vast community. The band of light is the combined glow of millions of distant stars, too faint to distinguish individually, but together forming a luminous river across the heavens. That sight is a reminder that you, too, belong to a galaxy, to a community of stars that has been evolving for more than 13 billion years. The galaxies also connect us to time. The light from distant galaxies has been traveling for billions of years to reach us. When we observe them, we are looking into the past, seeing them as they were long ago. In this way, the cosmos offers us both a history and a perspective. Are not only part of a galaxy, but also witnesses to the unfolding of galaxies across time. What is calming to realize is that galaxies endure. Stars within them come and go, but the galaxy as a whole persists. Even as galaxies merge and change, their essence remains. They are the long-lasting homes of stars, the steady frameworks within which cosmic evolution continues. Their existence gives structure to the universe, providing the spaces where life can emerge and where minds can reflect on their origins. To imagine galaxies is to feel both small and vast. You are one person, living on one planet, orbiting one star within one galaxy. And yet, that galaxy is itself part of a greater whole, connected to billions of others in the web of the cosmos. To hold this thought gently is to sense belonging not just to Earth, but to the Milky Way, to the universe itself. The birth of galaxies transformed the cosmos from scattered stars into organized communities. They provided the environment for stars to form steadily, for planets to emerge, and for life to eventually arise. They are the great containers of cosmic history, and within them, the story of the universe continues to unfold. As you rest with this reflection, imagine galaxies, not as remote objects, but as companions. Their light has traveled to you across time and space, offering a connection that is both distant and intimate. To notice this is to feel the calm rhythm of the cosmos, the enduring presence of galaxies as homes for stars, and the quiet reassurance that you, too, have a place within this vast community of light. Once galaxies began to take shape, stars continued to form within their gas clouds. These stars were not only sources of light and warmth, but also cosmic furnaces. In their cores, under immense pressure and heat, atoms collided and fused together, creating new elements. This process of nuclear fusion transformed the simple hydrogen and helium of the early universe into a richer palette of matter. From these fires came carbon, oxygen, nitrogen, and eventually the iron that runs through your blood. To feel this transformation, imagine a star as a balance between two great forces. Gravity pulls inward, trying to collapse the star, while the energy from fusion pushes outward, keeping it stable. Deep in the center, where the temperature rises to millions of degrees, hydrogen nuclei move so quickly that they can overcome their natural repulsion and fuse together. 4 hydrogen atoms merge into a single helium atom, releasing energy in the process. This energy streams outward, becoming the starlight that fills galaxies. As hydrogen is consumed, the core of a star changes. In larger stars, once hydrogen is depleted, the core contracts, heating up further. until it becomes hot enough for helium itself to fuse. Helium nuclei join to form carbon and oxygen, the essential ingredients for life. With each stage, heavier and heavier elements can be created as the star's core becomes hotter and denser. Nitrogen, neon, magnesium, silicon, all of these are born in the sequence of stellar fusion. This process, called nucleosynthesis, is one of the most profound rhythms of the universe. It shows how change arises naturally, step by step, from simplicity toward complexity. From the plain elements of hydrogen and helium, stars patiently craft the diversity of matter. Over millions and billions of years, the cosmos becomes enriched, preparing the way for planets, oceans, and living beings. It is soothing to reflect on the patience of stars. Fusion does not happen instantly. It unfolds slowly, steadily, over immense spans of time. A star like our Sun will shine for around 10 billion years, burning hydrogen quietly in its core. Larger stars live shorter but more intense lives, forging heavier elements before ending in dramatic deaths. Yet whether long or short, each star contributes to the gradual enrichment of the universe. The light you see in the night sky is evidence of this work. Each star you observe is actively fusing hydrogen into helium, releasing energy that travels across space. Some of those stars are also creating heavier elements deep inside, hidden from view but essential for the future. In this sense, the stars are not only beautiful to behold, they are creators, shaping the very materials from which you are made. Consider the oxygen in the air. Every breath you take depends on atoms forged in stars. Consider the calcium in your bones, the iron in your blood, the carbon in your cells. None of these existed in the first moments of the universe. They were crafted in the interiors of stars, released into space when those stars reached the end of their lives. You are not only surrounded by stardust, you are composed of it. The fire in the hearts of stars lives on in you. The process is guided by the laws of physics, unchanging across time and space. Fusion requires immense temperatures and pressures, which gravity naturally provides in stellar cores. The result is both energy and new matter, a combination that fuels cosmic evolution. It is not violent in its essence, but rhythmic, a steady beat of creation that continues across billions of years. Eventually, stars reach a limit. For stars up to the size of our Sun, fusion ends when the core fills with carbon and oxygen. The star sheds its outer layers gently, creating a planetary nebula, while the core remains as a white dwarf, slowly cooling. Larger stars, however, continue to fuse until they create iron. At that point, fusion no longer yields energy, and the balance between gravity and pressure collapses. These massive stars end their lives in supernova, scattering their newly forged elements across space. In those explosions, elements heavier than iron such as gold, uranium, and platinum are formed in an instant through rapid nuclear reactions. These supernova may sound dramatic, but in the calm rhythm of cosmic history, they are simply another step in the cycle of renewal. Without them, the universe would remain poor in diversity. With them, it becomes rich in possibility. Each supernova seeds its galaxy with heavy elements, enriching the gas clouds that will give birth to new stars and planets. Over generations, galaxies become more complex, and life becomes possible. Scientists confirm this story by studying the spectra of starlight. When light from a star is spread into a rainbow, dark lines appear at certain wavelengths, marking the presence of specific elements. In this way, astronomers can determine the chemical makeup of stars. They see hydrogen and helium in abundance, but also signatures of heavier elements. confirming that stars are the forges of matter. Observations of distant galaxies show the same pattern. The older the galaxy, the fewer heavy elements it contains, because it has not yet experienced many generations of stars. The evidence is consistent, painting a picture of gradual enrichment. Over cosmic time. What is calming to realize is that this process is universal. It happens in every galaxy, in every star-forming region, in every corner of the cosmos. Wherever stars exist, they are quietly shaping the matter that will become the foundation of future worlds. It is a rhythm that does not depend on us, but includes us, a steady unfolding that carries life forward. To rest with this thought is to feel connection. The fire in the hearts of stars is not remote. It is within you, in the elements that sustain your breath and heartbeat. When you look at the night sky, you are not only seeing stars, you are seeing the origin of yourself. The story of heavier elements is the story of your own body, your own life, written in the language of fusion. The birth of heavier elements also reveals a lesson in cycles. Stars create, release, and enrich. Their material becomes part of new stars, new planets, and eventually living beings. Nothing is wasted, nothing is lost. Matter circulates endlessly, transformed but continuous. The atoms that make you may once have been part of a star, part of another world, part of countless past forms. This cycle is both humbling and reassuring, a reminder of continuity in the midst of change. As you let these reflections settle, imagine the stars not as distant fires, but as companions in your own story. Their quiet work billions of years ago made possible the earth beneath you, the air around you, and the life within you. Their fires still burn, creating new elements that will shape future generations of planets and beings. In this vast rhythm, you are both a product and a participant. The hearts of stars are not only places of fusion, but also symbols of persistence. They shine steadily, sometimes for billions of years, holding balance against gravity, carrying out their quiet alchemy. In their patient endurance, there is a model of calm strength, a reminder that change can be slow, steady, and profound. To imagine the fire in the hearts of stars is to sense both heat and peace. Their flames are not destructive but creative, not chaotic but ordered. They bring forth the richness of matter, turning simplicity into diversity and emptiness into possibility. And as you rest now, you can feel held within that same rhythm, part of the great unfolding of the cosmos, shaped by the fire of stars, carried by its light, and enduring in its calm continuity. Stars, though long-lived, do not last forever. Each one is a balance between gravity pulling inward and the energy of fusion pushing outward. For smaller stars like our Sun, this balance can endure for billions of years. But for the most massive stars, the rhythm is shorter and more intense. They burn their fuel quickly, shining with great brilliance, but exhausting themselves in only a few million years. When such stars reach the end of their fuel, they face a profound transformation. They collapse and explode as supernova. A supernova is the death of a massive star, but it is also the birth of something new. As fusion in the core progresses, heavier and heavier elements are created: carbon, oxygen, silicon, and finally iron. But iron is different. Unlike lighter elements, fusing iron does not release energy. Instead, it consumes it. When the core of a massive star fills with iron, the balance between pressure and gravity collapses. In an instant, the core can no longer resist its own weight. The core falls inward, compressing to extraordinary densities. Temperatures rise to unimaginable levels. In less than a second, the collapse halts abruptly, and the outer layers rebound, rushing outward in a colossal explosion. This explosion is the supernova. It shines with a brilliance that can briefly outshine an entire galaxy. For weeks or months, the light of the supernova dominates the sky, visible across vast distances. Yet what may seem destructive is, in truth, profoundly creative. In the heat and violence of the explosion, new elements are forged. Gold, silver, uranium, and other heavy atoms are born in the chaos of collapsing matter. These elements are scattered across space, carried outward at incredible speeds. The star's material, once bound together, is released into the galaxy, enriching the surrounding gas clouds with a diversity of elements that will form new stars, new planets, and eventually life. In this way, supernovae are not ends, but transitions. They are the mechanism by which the universe recycles matter, transforming the ashes of one generation of stars into the seeds of another. Every star, every planet, and every living being carries within it the legacy of countless supernovae. The iron in your blood, the gold in your jewelry, the iodine in your body, all of it was forged in the death throes of ancient stars. To reflect on this is to sense both humility and belonging. The remnants of supernova take on different forms. For some, the collapsed core becomes a neutron star, a sphere only about 20 kilometers across, yet containing more mass than the sun. Neutron stars are among the densest objects in the universe. Their matter so compressed that protons and electrons merge into neutrons. If the star is even more massive, the collapse continues beyond any limit, creating a black hole. Both neutron stars and black holes are quiet witnesses to the power of gravity. Left behind after the brilliance of the explosion fades, the material expelled by supernova spreads outward, forming expanding shells of gas called supernova remnants. These remnants glow for thousands of years, enriched with heavy elements, mixing gradually with the interstellar medium. In time, this enriched gas becomes part of new star-forming regions. Within those clouds, new stars ignite, surrounded by planets built from the ashes of the past. Each generation carries the memory of those that came before. Scientists observe supernova both in our galaxy and in distant ones. Telescopes capture their light, revealing the fingerprints of elements within. The Crab Nebula, for example, is the remnant of a supernova observed on Earth in the year 1054. Its filaments of glowing gas still expand outward, evidence of the cycle of death and renewal. By studying these remnants, astronomers confirm the story. Supernova are the factories of heavy elements, and their material becomes part of new generations of stars. It is soothing to notice how this cycle mirrors rhythms in our own lives. Endings are not absolute. They create space for beginnings. The death of a star gives rise to the possibility of new worlds. The scattering of matter becomes the foundation of diversity. The cosmos teaches that nothing is wasted, that everything is transformed and carried forward. The light of supernova also connects us across time. When a supernova explodes in a distant galaxy, its light travels for millions or billions of years before reaching Earth. To see that light is to witness an event that happened long before humans existed, yet its echo still arrives, carrying information across the ages. The universe itself is a messenger, reminding us of the continuity of time. For new generations of stars, supernova are essential. Without the enrichment of heavy elements, planets like Earth could not exist. The first stars contained only hydrogen and helium, but after supernova, the cosmos gained carbon, oxygen, silicon, and iron. With these, rocky planets formed, oceans emerged, and life became possible. Every tree, every breath, every heartbeat depends on atoms created in the depths of stars. To reflect on this is to sense gratitude. The atoms that compose you are ancient, shaped in fires long before the earth was born. You are connected not only to the stars, but to their endings, to their willingness to release and transform. The universe has always carried within it this rhythm of creation through release, of life through death, of continuity through change. In the calm rhythm of cosmic history, supernovae are not interruptions, but notes in the larger melody. They appear, shine, release, and fade, leaving behind enrichment that ensures the song continues. Galaxies grow more complex because of them. Stars and planets become richer in diversity. Life finds its place because of the elements they scatter. As you rest with this thought, imagine the cycle unfolding gently. A massive star burns brightly, then releases itself in light and matter. Its elements drift into space, joining clouds of gas. From those clouds, new stars ignite, carrying the memory of the past within their cores. Around them, planets form, and on some of those planets, life arises. You are part of that sequence, a continuation of a rhythm that began billions of years ago. Supernovae are reminders that endings are not final. They are transformations necessary for renewal. The universe is not static, but dynamic, not fragile, but enduring. Through cycles of creation and release, it carries forward the materials of life, generation after generation. And as you breathe, now you carry within you the legacy of countless stars, the quiet fire of their lives, and the gentle release of their endings. Once the universe was enriched with heavier elements, carried outward by generations of stars and supernovae, new possibilities emerged. No longer was matter limited to hydrogen and helium. Now there were carbon, oxygen, silicon, and iron drifting in vast clouds of gas and dust. Under gravity's steady hand, these clouds began to collapse again, giving birth to new stars. But this time, something different happened. Around those stars, the leftover material did not disappear. It settled into disks, thin rotating planes of gas and dust. Out of these disks, planetary systems were born. The birth of a planetary system begins with a star. As the central core of gas ignites, its gravity pulls surrounding matter into orbit. Instead of falling directly inward, the material flattens into a spinning disk like a cosmic whirlpool. Within this disk, countless small particles collide and stick together. At first, they are no larger than grains of dust, but over time they gather into clumps, then rocks, then mountain-sized bodies. These growing fragments are called planetesimals, and they are the seeds of planets. The process is patient, unfolding over millions of years. Each collision builds something slightly larger. Some planetesimals shatter, but others survive, accumulating more material. Eventually, the largest ones grow massive enough to attract surrounding gas and dust with their gravity, accelerating their growth. Step by step, they become protoplanets, worlds in the making, still molten, still reshaping themselves, but destined to become stable planets. The diversity of planetary systems comes from the balance of conditions in each disk. Close to the star, temperatures are high, and volatile substances like water and methane cannot remain solid. In these regions, rocky planets form, built of metals and silicates. Farther from the star, where it is cooler, ices can survive. Here, giant planets take shape, their solid cores rapidly pulling in thick envelopes of gas, creating worlds like Jupiter or Saturn. Still farther out, icy bodies and comets form, drifting at the edges of the system. This structure can be seen in our own solar system. Mercury, Venus, Earth, and Mars are rocky planets, born close to the sun where only metals and rocks could endure the heat. Beyond them lie the gas giants Jupiter and Saturn, and the ice giants Uranus and Neptune, formed where ices could condense and collect. At the outer boundary, countless icy objects remain, relics of the early disk. This pattern is not unique. Observations of distant stars reveal similar systems, with rocky planets near their suns and giant planets farther away. One of the most remarkable discoveries of recent decades is the abundance of exoplanets, planets orbiting stars beyond our sun, with telescopes capable of detecting tiny dips in starlight or the subtle wobble of a star's motion. Astronomers have found thousands of such worlds. They come in every size and type: hot Jupiters circling close to their stars, super-Earths larger than our planet, and small rocky worlds that may resemble Earth itself. This diversity shows that planetary systems are not rare. They are a natural outcome of star formation, scattered throughout the galaxy. What is soothing to realize is that the process of planetary birth is gentle in its essence. Though collisions and impacts are part of the story, the underlying rhythm is one of gathering and orbiting, of material finding balance around a star. The planets that result are not accidents, but natural companions, formed from the same cloud as their parent star. Each system is a family, connected by shared origin and gravitational ties. Moons also arise in this process. Some form alongside their planets, condensing from smaller disks of gas and dust around young worlds. Others are captured, pulled into orbit by a planet's gravity. Still others form through impacts, when a collision ejects debris that later coalesces into a moon. In our own history, the moon likely formed when a Mars-sized body struck the young Earth, scattering material that later gathered into a single companion. Today, the moon still orbits us, a constant reminder of those early formative times. Planetary systems are not static. Over time, their orbits shift, influenced by gravity and by interactions with remaining gas. Some planets migrate inward or outward, changing the architecture of the system. Others are ejected entirely, wandering through interstellar space as rogue planets. Yet the overall pattern remains: stars with families of worlds, enduring for billions of years. For life, the formation of planets was essential. Without solid surfaces, without oceans and atmospheres, life as we know it could not arise. The Earth itself is a product of this cosmic process, a rocky planet enriched with carbon, oxygen, and water, orbiting at just the right distance from the sun. Our world is one example among countless others, but it carries the same heritage: the gathering of dust, the patience of collisions, the quiet work of gravity. Scientists continue to study the details of how planetary systems form. Observations of young stars often reveal disks of gas and dust, some with visible gaps carved by growing planets. These images are snapshots of creation, showing the process in action. They confirm what theory predicts: that planets are natural byproducts of star formation, arising wherever conditions allow. It is calming to reflect on the continuity. The atoms in your body, forged in stars, gathered into dust grains. Those grains joined into rocks, those rocks into planets. From that planet, Earth, life eventually emerged. The story of planetary systems is not distant from you. It is your own history, written on a cosmic scale. To imagine planetary systems is to see families of worlds orbiting in quiet harmony, circling their stars as the years pass. Some worlds are hot, others frozen. Some are barren, others may be fertile. All are part of the same rhythm of creation, the same unfolding that began with hydrogen and helium in the early universe. The birth of planets is a reminder that structure arises naturally. Dust becomes worlds, just as stars become galaxies. Nothing is wasted. Everything finds a place. The cosmos is not random but patterned, guided by gravity, cooled by expansion, enriched by generations of stars. In this pattern, planets are inevitable, as natural as starlight itself. As you rest with this thought, imagine countless systems across the Milky Way. Each star you see in the night sky likely has companions, invisible worlds circling in there. Darkness. Some may have oceans, mountains, or atmospheres. Others may be silent, barren rocks. All of them are part of the great story, the slow gathering of matter into families of worlds. You, too, belong to such a family orbiting the sun, with your earthly companions, part of the quiet rhythm of the cosmos. When we look up on a clear night, away from city lights, we can often see a hazy band stretching across the sky. It looks like a river of light, pale and delicate, threading its way through the stars. That band is the Milky Way, our home galaxy, seen from within. To understand its history is to explore the place where our solar system belongs, a vast community of stars and matter that has been forming and evolving for more than 13 billion years. The Milky Way, like other galaxies, began as a small gathering of matter in the early universe. After the Big Bang, slight ripples in density guided gravity to draw gas together. These regions became the seeds of galaxies. Our Milky Way likely started as a collection of small protogalaxies, each only a fraction of its current size. Over time, they merged, colliding and combining into something larger and more stable. This process of growth by merger is still visible today. The Milky Way continues to absorb smaller galaxies, folding them into its spiral arms, the earliest. Stars in the Milky Way were different from those we see now. They formed from hydrogen and helium, before heavier elements had become common. These stars, called population 2 stars, were less enriched, but they began the process of seeding the galaxy with metals through supernova. Their deaths filled the interstellar medium with carbon, oxygen, and iron, preparing the way for later generations of stars and for planets. Traces of these ancient stars can still be found in the halo of the galaxy, orbiting far from the central disk. Over billions of years, the Milky Way grew into a majestic spiral galaxy. It developed a flattened disk, where most of its stars lie, rotating in a grand, slow swirl. Spiral arms emerged, not as rigid structures, but as regions of density waves, where gas clouds are compressed and new stars are born. These arms are still visible today, glowing with the blue light of young, massive stars and the soft glow of nebulae. They are places of ongoing creation, where the galaxy renews itself continually. At the center of the Milky Way lies a dense bulge of stars, surrounding something even more mysterious, a supermassive black hole known as Sagittarius A*. With a mass about 4 million times that of the Sun, it quietly shapes the orbits of nearby stars. Though invisible, it anchors the galaxy's heart. Occasionally, bursts of energy reveal its presence when matter falls inward. For the most part, however, it rests silently, a calm center in a swirling community of stars. The Milky Way also has an extensive halo, an almost spherical region surrounding the disk. This halo contains ancient stars, globular clusters, and vast amounts of dark matter. The dark matter cannot be seen directly, but its gravity is essential. It provides the hidden framework that holds the galaxy together, preventing the outer stars from drifting away. Without it, the Milky Way's graceful spiral could not endure. Our solar system lies in one of the galaxy's spiral arms, the Orion arm, about 2/3 of the way out from the center. Here, we orbit the galactic core once every 225 million years. The stars you see in the night sky are companions in this orbit, fellow travelers around the center of the Milky Way. To realize this is to feel the scale of our motion. We are not fixed, but part of a vast rotation, carried along by the gravity of the galaxy, that the history of the Milky Way is written in its stars. Older stars, found in the halo and bulge, have fewer heavy elements. Younger stars, in the disk and arms, are richer, containing material recycled from previous generations. This gradient of composition tells the story of ongoing enrichment, of how the galaxy has grown more diverse with time. Every new generation of stars builds on the material left by those before, just as every chapter of a book builds on earlier pages. The Milky Way is not alone in its journey. It is part of the local group, a collection of galaxies bound together by gravity. The most prominent neighbor is the Andromeda Galaxy, a spiral even larger than our own. In about 4 billion years, the Milky Way and Andromeda will merge, forming a new galaxy. This future collision may sound dramatic, but on the scale of stars, it is gentle. Stars are so far apart that few will collide directly. Instead, their orbits will shift, and over billions of years, a new structure will emerge. The Milky Way's history is not finished. It is part of a continuing story of growth and transformation. Scientists study the Milky Way by observing its structure, mapping its stars, and measuring their motions. Telescopes like Dia have charted billions of stars, revealing streams of stars that are remnants of ancient mergers. These stellar streams show how the galaxy was built piece by piece, absorbing smaller galaxies over time. In this way, we can reconstruct its history, seeing not only where it is now, but how it came to be. It is soothing to realize that our galaxy is stable and enduring. Though stars are born and die, though galaxies merge and evolve, the Milky Way has existed for over 13 billion years and will continue for billions more. It is not fragile but resilient, holding within it the cycles of matter and energy that make life possible. To belong to the Milky Way is to be part of something ancient and secure. When you look at the night sky and see the band of the Milky Way, you are seeing not just stars, but history. The light reaching your eyes may have traveled for thousands of years, crossing the galaxy to meet you. Some of those stars are young, others ancient, but all are companions in the same vast system. The Milky Way is your home in the cosmos, not just a backdrop, but a place that nurtures life. To reflect on the Milky Way is to feel connection on many levels. You are connected to your Earth, to your Sun, and also to your galaxy. You share its motion, its history, its cycles of renewal. The atoms in your body were forged in stars of the Milky Way, carried by supernova into the clouds that formed the solar system. You are part of its fabric, as much as any star or planet. The history of the Milky Way is a reminder that creation is not a single event, but an ongoing process. Galaxies form, grow, merge, and evolve. Within them, stars and planets arise. Within those planets, life can appear. Each step builds on the last, in a rhythm that continues across cosmic time. To rest with this thought is to notice the calm unfolding of the universe, steady and enduring, carrying you along in its embrace. About 4.6 billion years ago, within one of the spiral arms of the Milky Way, a great cloud of gas and dust began to collapse. This cloud was not unique. Such clouds exist throughout the galaxy, drifting silently, shaped by gravity and turbulence. But this one, in a quiet region of the Orion Arm, was destined to become our home star. Its story is not just the history of a ball of gas. It is the beginning of the solar system, the foundation of Earth, and the source of energy that sustains every breath and heartbeat today. The cloud that gave birth to the sun was enriched by earlier generations of stars. Long before, massive stars had lived and died, scattering heavy elements into space through supernova. These elements, carbon, oxygen, silicon, iron mingled with hydrogen and helium, forming a mixture ready for new creation. Without those earlier stars, the sun could not have had the material to form planets, oceans, or life. The sun's birth was not an isolated event, but part of a cosmic cycle of enrichment. As the cloud collapsed, it flattened into a rotating disk, with most of the mass gathering at the center. Gravity pulled the gas inward, compressing it tighter and tighter, while conservation of angular momentum caused the disk to spin faster as it shrank. This balance of collapse and spin is a universal pattern in star formation. In the middle, matter collected into a dense, hot core, the protostar that would become the sun. Around it, the remaining disk of dust and gas began to form the seeds of planets. In the protostar's heart, temperatures rose to millions of degrees. At first, the heat came from gravitational compression as matter fell inward, but eventually the conditions became extreme enough for nuclear fusion to begin. Hydrogen nuclei merged to form helium, releasing energy in the process. This was the moment the sun truly ignited. From then on, the pressure of fusion balanced the pull of gravity, and the sun became stable. Its light streamed outward, announcing the arrival of a new star. The birth of the sun brought order to the surrounding disk. Radiation and solar winds pushed lighter materials outward, while heavier elements stayed closer to the center. This process helped shape the structure of the solar system. Rocky planets like Earth, Mars, and Venus formed near the sun, while gas giants like Jupiter and Saturn developed farther away. In this way, the sun's influence extended beyond light and heat. It sculpted the very architecture of its planetary family. The sun is an average star in many ways. It is a yellow dwarf, or G-type star, with a lifespan of about 10 billion years. But to us, it is extraordinary. Its energy sustains life, drives weather, powers ecosystems, and shapes every moment of our existence. Without the sun, Earth would be a frozen, lifeless rock. With it, our planet is warm, fertile, and filled with diversity. The sun is not only our star. It is our constant companion, the steady presence at the center of our days. To reflect on the sun's birth is to notice continuity. The hydrogen that fuels it was created in the first seconds of the universe. The heavier elements that form its planets came from earlier stars. Its light now sustains Earth, which, in turn, supports life. You are connected to this chain, part of the same unfolding. Every cell in your body depends on energy from the sun, captured by plants, stored in food, and transformed into the rhythms of life. The sun's story is also a lesson in balance. For billions of years, it has maintained equilibrium between gravity pulling inward and fusion pushing outward. This balance allows it to shine steadily, without sudden change, creating the stability necessary for life to flourish on Earth. In its patience, the sun models a calm strength, a reminder that great endurance comes from balance, not force. Scientists study the sun to understand both its origins and its future. By observing young stars in other regions of the galaxy, astronomers can see processes that mirror the sun's birth: collapsing clouds, glowing protostars, spinning disks of gas. These observations confirm that the sun's formation was not unusual, but part of a universal rhythm. Everywhere stars are born, planetary systems emerge, and new possibilities take shape. The sun itself carries traces of its history. Its composition reveals the mixture of elements from which it formed. Its light contains signatures of hydrogen and helium, as well as heavier elements inherited from ancient supernova. Even its motion through the galaxy tells us of its origin, as it orbits the Milky Way with its planetary family, part of a larger cosmic community. What is soothing to realize is that the sun is still young, about halfway through its life. It has already shone for 4.6 billion years and will continue for another 5 billion. This stability gives Earth a long window of habitability, a steady source of light and warmth. To rest with this thought is to feel the security of endurance. The sun's gentle presence will continue, unbroken, for billions of years to come. In time, of course, the sun will change. It will eventually exhaust its hydrogen and expand into a red giant, engulfing the inner planets. Later, it will shed its outer layers, leaving behind a white dwarf that will cool slowly into darkness. But that future is far away, measured in billions of years. For now, and for countless generations to come, the sun will shine steadily, offering its light and warmth. The birth of the sun was the birth of our possibility. Without it, there would be no Earth, no oceans, no life. Its light connects us to the beginning of the universe, to the fusion of hydrogen into helium, to the cycle of stars enriching galaxies. To imagine its birth is to see your own origins, not in myth or story, but in the calm unfolding of cosmic processes. As you rest with this reflection, imagine the sun not only as a star in the sky, but as your companion in existence. Its birth was the turning of a page in cosmic history, leading directly to you. Its light falls on your skin, warms your days, and sustains your life. You are not separate from the sun. You are part of its story, written in its fire, carried in its light, and held within its calm endurance. Around 4.6 billion years ago, as the sun was settling into its long life of steady shining, the material that surrounded it began to gather into new forms. The cloud of gas and dust that gave birth to the sun still held vast amounts of matter, swirling in a disk around the young star. Within this disk, countless grains of dust and ice moved in slow orbits, colliding gently, sticking together, and beginning the long process that would eventually create planets. One of these worlds, after a journey of transformation, would become Earth. At first, the process was delicate. Dust grains, no larger than specks of smoke, collided and clumped. Electrostatic forces helped them stick, forming small aggregates. Over time, these clumps grew into larger bodies, stones and boulders, drifting in orbit around the sun. Collisions became more frequent, and as bodies grew, gravity gave them an advantage. Larger objects pulled in smaller ones, growing faster and faster. Within a few million years, some of these protoplanets were already hundreds of kilometers wide. In the region where Earth was forming. The heat from the nearby sun allowed only metals and rocks to remain solid. Lighter materials, such as water and methane, evaporated or were pushed outward into the colder reaches of the disk. As a result, the inner planets Mercury, Venus, Earth, and Mars formed from rocky and metallic elements. Earth's foundation was therefore solid, built from silicates and iron, collected patiently from the disk of dust. The young Earth was not calm in its beginnings. It grew through constant collisions, each one releasing energy. The surface was molten, oceans of magma covering the planet. Heavier materials like iron and nickel sank inward, forming the core, while lighter materials floated upward to create the mantle and crust. This process of differentiation gave Earth its layered structure, with a metallic heart, a rocky body, and eventually, a thin surface where continents and oceans would form. One of the most dramatic events in Earth's early history was the impact that likely created the Moon, a protoplanet about the size of Mars, sometimes called Theia, collided with the young Earth. The impact was catastrophic, melting large parts of both bodies. Debris was thrown into orbit, and over time, that debris gathered into a single large companion, the Moon. This collision shaped Earth profoundly, tilting its axis, stabilizing its rotation, and influencing the tides that would later guide the rhythms of life. Even today, the Moon is a constant reminder of that formative encounter. As Earth cooled, volcanic activity released gases trapped inside. Carbon dioxide, nitrogen, and water vapor poured into the early atmosphere. At first, the air was thick and unbreathable, lacking oxygen, but it formed a blanket that held warmth and allowed water to condense. Clouds gathered, and for the first time, rain fell. Over countless years, the rain collected into basins, filling the surface with oceans. With oceans came stability, a reservoir for heat and chemicals, a cradle for the beginnings of life. The presence of liquid water made Earth unique among the inner planets. Mercury was too close to the sun, and any water quickly boiled away. Venus became a furnace, with a dense atmosphere trapping heat in a runaway greenhouse effect. Mars, smaller and with weaker gravity, lost much of its atmosphere, leaving it cold and dry. Earth alone held the right balance, the right distance from the sun, the right mass to hold an atmosphere, and the right conditions for water to remain liquid. This balance, sometimes called the habitable zone, made Earth a rare and precious world. The early atmosphere and oceans also set the stage for chemistry to grow more complex. Minerals dissolved in water, volcanic gases mixed with sunlight, and organic molecules began to form. Though life had not yet appeared, the ingredients were assembling. The Earth was preparing its surface for the next great transition, from chemistry to biology. Scientists study Earth's formation through many clues. Meteorites, remnants of the early solar system, contain primitive material that shows what the building blocks of Earth were like. The oldest rocks on Earth, found in ancient cratons, reveal the planet's early crust. Lunar samples brought back by astronauts preserve a record of the Moon's formation, which in turn reflects Earth's own violent youth. Together, these pieces tell a consistent story. Earth formed through accretion, differentiation, impact, and cooling until it became the stable world we know. It is soothing to realize how patient this process was. From dust grains to oceans, took hundreds of millions of years. Nothing was rushed, nothing skipped. Step by step, the Earth found its form, guided by natural laws, shaped by time. The same gravity that holds you to the ground today was at work then, gathering the planet together. The same chemistry that flows in your cells began in those ancient oceans. You are part of this continuity, connected to the very formation of the world beneath your feet. The formation of Earth is also a story of resilience. Despite violent impacts and molten beginnings, the planet stabilized. Despite a chaotic youth, it cooled, calmed, and grew capable of nurturing life. To reflect on this is to sense security. Earth has endured for billions of years, and its foundations are strong. You walk on ancient stone, breathe air that has cycled through eons, and drink water as old as the planet itself. When you stand on Earth today, you are standing on a world that is the product of countless transformations. It began as dust, became rock, endured fire, created oceans, and stabilized into balance. Its history is long, but its presence is immediate. Every breath, every step. Every moment is part of that 4.6 billion year journey. To imagine Earth's formation is to sense the calm rhythm of cosmic creation. Nothing was wasted. Every step led to the next. Dust became rock, rock became planet, planet became home. The Earth carries within it the memory of stars, the scars of impacts, and the softness of rain. And you are part of that memory, living on its surface, carried in its orbit, nourished by its oceans and air. As you rest with this reflection, notice the security that comes from knowing your world's deep history. The ground beneath you is not fragile, but enduring, shaped by time into a stable home. The Earth's formation was the foundation for everything you know, for life itself. You are not separate from it. You are its continuation, a being of Earth, shaped by its elements, held by its gravity, and part of its calm and steady story. Once Earth had cooled enough for oceans to form, the stage was set for a new chapter of cosmic history. The atmosphere was dense with gases from volcanic activity, carbon dioxide, nitrogen, water vapor, and traces of methane and ammonia. Lightning flashed through clouds. Ultraviolet light from the young sun reached the surface, and hydrothermal vents at the ocean floor released heat and minerals. In this environment, chemistry grew more complex. Molecules joined together, broke apart, and reformed until gradually something remarkable happened. The first signs of life appeared. Life did not emerge in a single moment, but as a long, patient sequence of steps. At first, simple organic molecules formed amino acids, nucleotides, and sugars. Experiments on Earth have shown that such molecules can arise naturally under conditions like those of the early planet. Lightning, ultraviolet radiation, and volcanic activity provide the energy, while water offers a medium where reactions can take place. Step by step, chemistry produced the ingredients needed for biology. These molecules began to assemble into larger structures. Amino acids linked into proteins, capable of folding into shapes that carried out basic functions. Nucleotides joined into strands, precursors of RNA and DNA, molecules capable of storing information. Lipids, with their water-repelling properties, formed tiny bubbles, creating compartments that could separate inside from outside. Within these compartments, reactions could concentrate, setting the stage for self-sustaining systems. One of the most important transitions was the appearance of molecules that could replicate. Among them, RNA is thought to have played an early role. RNA can both store information and catalyze chemical reactions, a rare combination that may have allowed the first primitive life to emerge. Once replication began, variation followed. And with variation came the possibility of natural selection. The first steps of evolution had begun. The exact details of life's origin remain uncertain. Scientists propose different settings: shallow ponds where sunlight and evaporation could concentrate molecules, hydrothermal vents where minerals and heat created stable environments for reactions, or even icy surfaces where freezing could help molecules link together. Perhaps life arose in more than one place, with different experiments happening simultaneously. What unites these possibilities is the idea that life emerged naturally, as a continuation of the chemistry of the universe, by about 3.8 billion years ago. Evidence shows that life already existed on Earth. Fossilized microorganisms appear in ancient rocks, and chemical traces suggest biological activity. These earliest forms were simple, single-celled organisms without nuclei, similar to today's bacteria. They lived in the oceans, drawing energy from sunlight, from minerals, or from chemical gradients. Though simple, they were resilient, adapting to the changing planet and laying the foundation for all later life. It is soothing to reflect on how patient and gradual this process was. From atoms to molecules, from molecules to cells, the journey took hundreds of millions of years. Nothing was rushed. Each step prepared the way for the next. The same physical laws that guided the formation of stars and planets also guided the chemistry of life. The universe did not create life in haste. It unfolded it gently, in rhythm with time. Life brought something new to the earth, the ability to transform the planet itself. Early microorganisms released oxygen as a byproduct of photosynthesis, gradually changing the composition of the atmosphere. At first, this oxygen was absorbed by rocks and oceans, but eventually it accumulated in the air, creating conditions for more complex life forms. This process, called the Great Oxidation Event, was a turning point in Earth's history, all initiated by the quiet work of tiny cells. The emergence of life is also the emergence of continuity. Every living thing today descends from that first population of cells. The DNA in your body carries instructions that can be traced back through billions of years of replication. The proteins in your cells fold in ways first discovered by ancient life. The water in your blood echoes the oceans where life began. You are connected to that moment, part of an unbroken lineage stretching back to the dawn of biology. Scientists continue to search for clues to life's origins. They study ancient rocks, simulate early Earth in laboratories, and explore environments like deep-sea vents that may resemble those of the past. They also search other planets and moons, wondering whether similar processes might have unfolded elsewhere. Mars, Europa, and Enceladus all show signs of water and chemistry, raising the possibility that life is not unique to Earth. The emergence of life here suggests it may be a natural outcome of the universe, given the right conditions. What is calming to realize is that life is part of the universe's unfolding, not an exception to it. Just as stars form naturally from gas and planets from dust, so life arises naturally from chemistry. You are not apart from the cosmos, but one of its expressions, a continuation of its creativity. The atoms in your body once drifted as gas in space, then formed Earth, then joined into molecules, and finally became alive. To rest with this thought is to feel your place in a vast, ongoing story. The first life was small, fragile, and simple, yet it endured. Over time, it diversified, adapted, and spread, filling every niche the Earth offered. From those beginnings came the forests, oceans, and animals of today. From those beginnings came humans, capable of reflecting on the origins of life itself. All of it traces back to that quiet emergence in the ancient oceans. To imagine the emergence of life is to feel wonder and peace. It was not sudden or miraculous in a disruptive sense, but gentle, gradual, and patient. Life grew out of Earth's chemistry as naturally as stars grew out of galaxies. And as you breathe now, you continue that story, carrying within you the molecules, the instructions, and the rhythms that began billions of years ago. Once the first living cells appeared on Earth, the story of life did not stand still. It began to change, slowly but persistently, over billions of years. Evolution is the process by which life adapts, diversifies, and transforms. Guided by natural selection and by chance, simple organisms gradually gave rise to more complex ones, filling the Earth with variety. To reflect on this process is to sense the patient rhythm of time, carrying life forward in waves of transformation. For the first billion years, life remained simple. Microorganisms similar to bacteria dominated the oceans. They lived in countless numbers, feeding on minerals, sunlight, or chemical reactions. Though small, they were resilient, able to survive in extreme heat, acidity, or cold. These microorganisms established the basic cycles of the Earth, recycling carbon, nitrogen, and sulfur, and slowly shaping the atmosphere. A great transformation came with photosynthesis. Some microorganisms developed the ability to capture sunlight and use it to produce energy. In the process, they released oxygen as a byproduct. At first, this oxygen reacted with minerals in the oceans and crust, but over time, it began to accumulate in the atmosphere. Around 2.4 billion years ago, during what is called the Great Oxidation Event, oxygen levels rose significantly. This was a turning point. Oxygen is highly reactive, and it allowed for new, more efficient forms of metabolism. At the same time, it also caused the extinction of many organisms that could not tolerate it. Life had transformed the planet, and in doing so, transformed itself. With oxygen in the air, new possibilities opened. Cells developed more complex structures, with internal compartments and nuclei. These eukaryotic cells were larger, more versatile, and capable of forming multicellular organisms. This step was profound, for it allowed life to grow beyond single cells. With multicellularity came cooperation, specialization, and greater diversity. Organisms could grow larger, develop tissues, and adapt to new environments. About 600 million years ago, another great transformation occurred, the Cambrian explosion. In a relatively short span of geological time, life diversified dramatically. The oceans filled with new forms animals, with shells, spines, and segmented bodies. Many of the basic body plans we know today emerged during this period. Evolution had accelerated, exploring countless possibilities, many of which still endure in the forms of fish, insects, and mammals. Life did not remain confined to the oceans. Around 400 million years ago, plants began to colonize land, followed by insects and animals. Forests spread across continents, creating new habitats. Amphibians evolved from fish, reptiles from amphibians, and eventually mammals and birds. Each step was gradual, guided by adaptation to changing conditions. Through extinctions and renewals, life persisted, finding new forms again and again. Mass extinctions were part of this rhythm. At several points in Earth's history, sudden events, volcanic eruptions, climate shifts, or asteroid impacts wiped out large portions of life. The most famous was the extinction of the dinosaurs 66 million years ago, caused by an asteroid strike. Yet each extinction cleared the way for new forms to arise. Mammals, once small and overlooked, flourished after the dinosaurs' decline, eventually giving rise to primates and humans. Even in loss, evolution found renewal. What is calming to realize is that evolution is not a ladder, but a branching tree. Life does not move toward a single goal, but explores many paths, some leading to enduring success, others ending in extinction. The diversity of life on Earth is the result of countless experiments carried out over billions of years. You are part of one branch of that tree, connected to every living thing by shared ancestry. The DNA in your cells carries instructions inherited from the earliest life, modified but continuous. The great transformations of life are written in fossils, rocks, and genes. Fossils show the shapes of ancient creatures, from trilobites to dinosaurs. Rocks preserve chemical signatures of past atmospheres. Genes reveal the shared code linking all organisms. Together, these records confirm the story. Life has been evolving for billions of years, with continuity and change woven together. It is soothing to reflect on the patience of this process. Life's transformations were not sudden leaps, but gradual steps unfolding over vast spans of time. The complexity of today's ecosystems arose from small changes accumulated steadily. This rhythm mirrors the rhythm of your own life. Change is slow, but over time it becomes profound. Evolution also shows resilience. Despite mass extinctions, shifting climates, and dramatic changes, life has persisted. It adapts, diversifies, and continues. The forests, oceans, and creatures around you are the current expression of this resilience. You, too, are part of it, a being shaped by billions of years of adaptation. When you look at life today, the flight of birds, the growth of trees, the complexity of human thought, you are seeing the outcome of these great transformations. Each breath you take depends on oxygen first released by ancient microorganisms. Each movement of your body depends on cells that evolved from simple ancestors. Each thought arises from a brain shaped by the long history of mammals. You carry within you the entire story of evolution, written in your genes and expressed in your form. The emergence and evolution of life show that complexity can grow from simplicity and diversity from unity. They reveal that change is not to be feared, but embraced as part of the natural rhythm. To rest with this thought is to sense your connection to all of life, to the oceans that gave birth to it, to the forests that nurtured it, and to the creatures that share your world. As you breathe now, you are participating in the same cycles that began billions of years ago. The oxygen in your lungs is a gift of ancient photosynthesis. The cells in your body are descendants of the first cells. The resilience you feel is the resilience of life itself, tested and renewed across eons. To reflect on evolution is to feel both small and vast. Small in the span of time, yet vast in the depth of connection. You are part of an unbroken chain of life stretching from the first cells to the present moment. You are a continuation of Earth's great transformations, a living expression of its calm, enduring creativity. For billions of years, life on Earth unfolded without us. Oceans filled with microorganisms, forests rose and fell, animals walked, flew, and swam, long before humans appeared. We are newcomers in the vast story of the universe. And yet, when we arrived, something different began to unfold. A new dimension of awareness, the ability not only to live, but to reflect on life, to ask questions, and to imagine the cosmos itself. Our story begins with primates, mammals adapted for life in trees, with grasping hands and forward-facing eyes. From this foundation, over millions of years, hominins emerged in Africa. They walked upright, freeing their hands for tools and gestures. They lived in groups, sharing food and protection. Their brains grew larger, their communication more complex. Each step was gradual, but together they opened the way toward humanity. The earliest members of our lineage were simple compared to us, but they carried the seeds of what would become language, culture, and imagination. They made stone tools, controlled fire, and spread into new environments. Over time, different species of humans arose: Homo habilis, Homo erectus, Neanderthals, and others, each exploring different paths. Some lived for hundreds of thousands of years before fading, while others, like Homo sapiens, continued and expanded. Homo sapiens, our own species, appeared around 300,000 years ago. At first, we were small bands of hunter-gatherers, living close to the rhythms of nature. We followed animals, gathered plants, and created tools from stone, bone, and wood. Slowly, culture developed. We painted on cave walls, carved figures, and buried our dead with care. These acts reveal something beyond survival, a sense of meaning, of beauty, of connection to something larger. The capacity for language allowed humans to share knowledge across generations. Unlike instinct alone, language gave us the ability to teach, to remember, to dream collectively. Stories carried lessons, myths shaped identity, and words bound communities together. Through language, humanity wove its memory into a fabric that could endure and grow. Another transformation came with agriculture. About 10,000 years ago, humans began to cultivate plants and domesticate animals. This shift allowed permanent settlements, villages, and eventually cities. Populations grew, and with them came new complexities: trade, writing, law, and art. Civilizations rose, with temples, palaces, and libraries. Humanity's footprint on Earth deepened, shaping landscapes and ecosystems. Yet through all these changes, humans remained part of nature. Our bodies still carry the imprint of our evolutionary past, the structure of our hands, the beating of our hearts, the needs of our cells. We are not separate from the Earth, but expressions of it, shaped by its cycles, dependent on its balance. To reflect on humanity is not only to see our achievements, but also to recognize our roots in the long continuity of life. What distinguishes humans is not strength or speed, but awareness. We can imagine futures, reflect on the past, and wonder about our place in the universe. We look at the night sky and ask where it all began. We create art and music, expressing feelings that go beyond survival. We build sciences, seeking to understand the laws of nature. And now, we can even tell the story of the cosmos itself, tracing our origins from the Big Bang to the present moment. This awareness carries both beauty and responsibility. Humans have transformed the Earth more than any other species. We have harnessed energy, reshaped landscapes, and altered the climate. We have built machines, cities, and networks that connect the planet. With this power comes the need for wisdom, the capacity to care for the world that sustains us. The awareness that sets us apart also calls us to responsibility. It is soothing to remember that, despite our complexity, we remain deeply simple in our essence. We breathe, eat, and rest, like all creatures. We are nourished by the same sun, sustained by the same water, and carried by the same earth. Our awareness does not separate us, but connects us more deeply, allowing us to see our kinship with all life. Every plant, every animal, every person is part of the same unfolding story. The story of humanity is also a story of resilience. Our ancestors faced ice ages, droughts, and migrations across continents. They endured scarcity, conflict, and uncertainty. Yet they survived, adapted, and grew. Their endurance is within you, written into your genes, and carried in your breath. You are the continuation of their strength, their creativity, and their hope. In the grand timeline of the cosmos, humanity is recent. If the history of the universe were a single year, humans would appear only in the final minutes of December 31st. And yet, in that brief moment, we have become aware of the entire year. We can imagine the Big Bang, the birth of stars, the formation of galaxies, and the emergence of life. The universe has, through us, become conscious of itself. To reflect on humanity is to sense wonder. You are a being of stardust, shaped by evolution, aware of your own existence. You carry within you the memory of stars and the creativity of life. You belong to a species that asks questions, tells stories, and seeks meaning. You are both fragile and powerful, small in the cosmos yet vast in awareness. As you rest with this thought, notice the calm presence of your own breath. Inhale and exhale, part of the same rhythm that connects you to all of life. Humanity's story is not separate from the Earth or the cosmos. It is one chapter in the great unfolding, a chapter that continues with you. You are both an individual and part of a collective, both temporary and timeless. Both body and awareness. Humanity, in its essence, is the universe reflecting on itself. To imagine this is to feel both humility and peace. You are not apart from the cosmos, but an expression of it, aware and alive, carrying forward the calm, enduring story of existence. For most of human history, the cosmos was a mystery observed with awe. People looked at the night sky and saw patterns of stars, weaving them into myths and stories. The Milky Way was imagined as a river of light, constellations as animals, or heroes. The sun and moon marked the rhythms of time, guiding agriculture, rituals, and calendars. In every culture, the heavens inspired meaning. Yet the true scale and nature of the universe remained hidden. The modern era brought a new way of seeing science. Science is not only a body of knowledge, but a method of asking questions, testing ideas, and refining understanding. Step by step, over centuries, humans have built a clearer picture of the cosmos. This process, though complex, is also gentle in its rhythm. Each discovery grows from what came before, and each correction brings us closer to truth. The story of modern discovery began with simple observations. Ancient astronomers tracked the motions of planets, noticing their wandering paths among the stars. In time, telescopes revealed more detail: craters on the moon, moons around Jupiter, rings around Saturn. Galileo, in the 17th century, looked through his telescope and saw that the heavens were not perfect spheres, but places of variety and motion. This was a profound shift, showing that Earth was not the center of all things, but part of a larger system Isaac Newton later described: the laws of motion and gravity, showing that the same force that pulls an apple to the ground also governs the orbits of planets. This unity of laws connected the earth and sky, revealing that the cosmos follows the same principles everywhere. With this realization, the universe became not only vast, but understandable. In the centuries that followed, new tools extended our reach. Telescopes grew larger, spectroscopes revealed the chemical makeup of stars, and photography captured faint galaxies. In the 20th century, radio telescopes opened new windows, detecting signals invisible to the eye. Today, observatories orbit Earth, floating above its atmosphere, capturing light from the farthest reaches of space. Each advance has brought deeper clarity, like layers of fog lifting to reveal a landscape. One of the most important discoveries was the expansion of the universe. In the 1920s, Edwin Hubble observed that galaxies are moving away from us, and that the farther they are, the faster they recede. This revealed that the universe is not static, but expanding. From this expansion came the realization of the Big Bang, the idea that the cosmos began in a hot, dense state billions of years ago. With careful measurement, scientists traced its age to about 13.8 billion years. Another great discovery was the cosmic microwave background. In 1965, two scientists, Arno Penzias and Robert Wilson, detected faint radio noise coming from every direction in the sky. At first, they thought it was interference, even cleaning their antenna to remove what they imagined was a source of contamination. But the signal remained. It turned out to be the cooled afterglow of the early universe, the light released when the first atoms formed. This discovery confirmed the Big Bang theory, giving us a direct glimpse of the cosmos's childhood. Modern science has also revealed the invisible. By studying the motions of galaxies, scientists discovered that most of the mass in the universe cannot be seen. They call it dark matter, a mysterious substance that interacts with gravity, but not with light. Even more puzzling is dark energy, a force that drives the acceleration of the universe's expansion. Together, dark matter and dark energy make up about 95% of the cosmos, reminding us that our understanding is still incomplete. Closer to home, science has transformed our view of the solar system. Space probes have flown past planets, landed on moons, and sent back images of landscapes never seen before. We have watched volcanoes erupt on Io, storms swirl on Jupiter, and geysers spray from the surface of Enceladus. We have touched the dust of comets and traced the icy plains of Pluto. Each mission expands our sense of connection, showing that the solar system is not abstract, but real, tangible, and full of wonder. The discovery of exoplanets' worlds orbiting other stars has deepened this sense of connection. Thousands have now been found, some rocky like Earth, some gas giants, some orbiting in the habitable zones where liquid water might exist. These discoveries suggest that planetary systems are common, and that the conditions for life may be widespread. The question of whether life exists elsewhere remains open, but the possibility alone reshapes our sense of belonging. Science also allows us to look inward to understand ourselves. By studying DNA, scientists have traced the unity of life on Earth, showing that all living beings share common ancestry. By studying fossils, they have reconstructed the branching tree of evolution. By studying the brain, they explore the roots of consciousness. These insights show that we are not separate from nature, but continuous with it. Bound by the same laws that govern stars and galaxies. It is soothing to reflect on the nature of discovery. Science is not about sudden leaps, but about steady progress. Hypotheses are tested, evidence is weighed, and understanding grows gradually. Mistakes are corrected, and ideas evolve. This rhythm mirrors the rhythm of the universe itself, patient, enduring, always unfolding. The story of science is part of the story of life, another way in which the cosmos expresses awareness. The modern era has also given humanity new tools for reflection. Images from space show Earth as a blue sphere, fragile and beautiful, floating in darkness. The pale blue dot photograph, taken by Voyager 1 from the edge of the solar system, shows our planet as a tiny speck of light, less than a pixel in size. This view humbles us, reminding us of our smallness and our unity. All of human history has unfolded on that dot, surrounded by the vastness of space. Yet science does not diminish wonder. Instead, it deepens it. To know that the stars are suns, that galaxies are vast communities of stars, that atoms in our bodies were forged in ancient supernova, these truths are as beautiful as any myth. They show that reality itself is wondrous, beyond invention. To rest with this thought is to sense calm amazement. The cosmos is vast, but it is knowable, and we are part of its unfolding. The modern era of science and discovery is still young. Telescopes are being built that will see farther than ever before. Missions are planned to Mars, Europa, and beyond. Experiments seek to reveal the nature of dark matter and dark energy. Each discovery will bring new questions, continuing the rhythm of curiosity. The story is not finished. It is ongoing, open, and alive. As you breathe now, you are part of this moment in the universe's history. You are a human being living on Earth with the ability to look up and ask questions, to build tools that extend your senses, and to share discoveries with others. You are both small in scale and vast in awareness, connected to the stars by matter, to life by ancestry, and to knowledge by curiosity. The modern era reminds us that awareness itself is part of the cosmos. Through you, the universe observes, reflects, and learns. Science is not apart from nature, but one of its expressions, a continuation of the creativity that began with hydrogen, stars, and galaxies. To reflect on this is to feel peace. The cosmos is not silent, for it speaks through discovery, and you are part of its voice. The universe, as we see it now, is still young compared to what lies ahead. It has expanded for 13.8 billion years, a long stretch by human measure, yet only the opening chapters of a story that will continue for trillions of years and beyond. To look ahead is not to predict with certainty, but to imagine gently, guided by the rhythms of physics and the patterns we observe today. The future of the universe is not rushed. It is patient, unfolding in scales of time that are almost beyond comprehension. In the near future, measured in billions of years, the cosmos will look much as it does now. Stars will continue to form in galaxies, planets will orbit their suns, and life may arise on other worlds, as it did on Earth. Our own sun, halfway through its life, will continue to shine steadily for another 5 billion years. For now, and for countless generations, it will remain a constant presence, offering warmth and light. Yet even stars have lifetimes. In about 5 billion years, the sun will exhaust the hydrogen in its core. It will expand into a red giant, engulfing Mercury and Venus, and perhaps Earth as well. Its outer layers will be shed into space, glowing as a planetary nebula, while its core will contract into a white dwarf, a small, dense ember cooling slowly over time. Other stars across the galaxy will follow similar paths, each according to its mass. The cosmos will gradually grow older, its stars aging and fading in the distant future. New stars will still be born, but at a slower pace. Galaxies use their reservoirs of gas to form stars, but those supplies are not infinite. Over tens of billions of years, star formation will decline. The galaxies will become quieter, filled with aging stars, fewer new lights kindling in their arms. The universe will remain luminous for a long time, but gradually, the night skies will dim. Galaxies themselves will also change. The Milky Way and Andromeda, our nearest large neighbor, are moving toward each other. In about 4 billion years, they will merge, forming a new galaxy sometimes called Milkomeda. To human imagination, a galactic collision sounds dramatic, but on the scale of stars, it is gentle. Stars are so far apart that few will collide directly. Instead, their orbits will shift, and over billions of years, a new spiral or elliptical structure will emerge. The night sky then, for any beings who might see it, will be filled with streams of stars from 2 galaxies woven into one dot as time stretches further. Beyond trillions of years, most stars will exhaust their fuel. White dwarfs will cool into black. Dwarfs, faint remnants of what once shone. Neutron stars and black holes will remain, quiet witnesses of stellar deaths. The universe will become a place of faint glows and dark remnants, a quieter version of itself, dark energy. The mysterious force driving the acceleration of the universe's expansion will also shape the future. As expansion continues, galaxies will drift farther apart. Eventually, most galaxies beyond our local group will slip beyond the observable horizon, their light stretched so much by expansion that it can never reach us. To any observers then, the universe will seem emptier, with fewer galaxies visible. Though they are still there, beyond reach. In unimaginably distant times, the cosmos may enter what is called the heat death or big freeze. In this scenario, stars have long since burned out, Black holes have evaporated through Hawking radiation, and the universe is filled with thin, cold radiation, spread so evenly that nothing new happens. This is not a dramatic end, but a slow, fading, a settling into stillness. The cosmos will not vanish, but it will grow quiet. Like a long exhale into silence, other possibilities exist, whispered by theory. Some suggest the universe might one day collapse in a big crunch, reversing its expansion. Others imagine cycles of expansion and contraction, an endless rebirth. Some propose a big rip, where dark energy grows so strong that it tears galaxies, stars, and even atoms apart. Each of these futures depends on the true nature of dark energy, which remains a mystery. For now, the most supported view is the quiet, steady cooling of the big freeze. It is soothing to notice that these futures, though immense, do not threaten us in any immediate way. They unfold on scales so vast that even the entire history of humanity is but a blink within them. The Earth, the Sun, and the Milky Way will continue for billions of years. Life, in one form or another, may have opportunities far beyond our imagining. The distant fates of the cosmos are not concerns to hold, but reflections to rest upon, gentle reminders of scale. The future of the universe also carries beauty. Stars that will be born tomorrow will shine for billions of years, illuminating planets yet unseen. Civilizations may arise, wonder about their origins, and gaze at their skies as we do now. The cycle of curiosity may continue, even as the stars themselves fade. The cosmos is not only a place of matter and energy, but of awareness carried forward, wherever life and thought can emerge. For you, in this moment, the future of the universe is not something to fear, but something to accept as part of the great rhythm. Just as the Big Bang was not a violent blast, but a quiet unfolding, so too will the end be not a sharp event, but a gradual transformation. The cosmos has always carried within it continuity, change, and endurance. You are part of that same flow. As you breathe, notice how the rhythm of your body echoes the rhythm of the universe. Expansion and release, gathering and letting go. The stars expanded from hydrogen into heavier elements, released them into space, and began again. The universe itself expands, cooling, softening, and unfolding toward new states. You are not apart from these rhythms. You are one with them. The gentle look ahead reminds us of humility. Our lives are brief, yet within them we can hold the entire story, from the Big Bang to the far future. We can imagine what the universe will become, even if we will not see it. This capacity for awareness is itself part of the cosmos, as natural as starlight, as enduring as gravity. To reflect on the future of the universe is to rest in perspective. You are small in scale, yet vast in connection. You belong to a cosmos that began with light, continues with life, and stretches into the deep future. Its fate is not separate from you, but includes you, just as your atoms, your breath, your awareness are part of its unfolding. As you settle into this thought, allow yourself to feel the peace of continuity. The cosmos has endured for billions of years and will endure for billions more. You are here now, a moment of awareness within it, carried by its calm expansion. Whatever the far future may hold, new stars, fading galaxies, or the quiet of heat, you are part of that story, as steady and connected as the stars themselves. This was the Sleepy Brain Dose. Thank you for sharing this calm journey through the cosmos. May the rhythm of the universe, from the first light to the stars above you now, bring you peace. As you close your eyes, let the quiet vastness carry you into rest. Until next time, sleep well and dream softly among the stars.